So this is more getting on the level with y'all rather than an instructive piece. And I wanted to talk a little bit about, do you need to know stats? And this has been a conversation I've had with a lot of students over the last few years and a lot of the faculty, and we kind of throw this back and forth. The short answer is yes, you do, but the degree to that and the degree to which we expect it is tricky. And what does it mean to quote unquote know stats? And so I wanted to talk a little bit about that, about what is statistical analysis, which hopefully you know at least in very broad strokes, but I'm going to restroke that in broad strokes, and then how do you get there? But this is within the context of this particular program, where the initial vision of this program, and this was a couple of faculty members at ASU, and I think I'm the only surviving one in SDS that kind of was thinking about this. We have some in other programs, where we were trying to say, okay, can we bring in people from computer science and from the technical backgrounds, and the people from the social science, and for the people from the social sciences, give them enough of the technical piece and the context, and for the people from the we've had people that came out of, say, computer science or from engineering, can we give them enough of the social theory that they can kind of come together and work on stuff, right? And that has always been part of the vision, which is that often these are two camps that can't talk to each other. And there's, outside of the very specific issues around social data science, around data science more broadly, around artificial intelligence, around that kind of focused area, very broadly within organizations, there are a dearth of people that can speak tech and speak real life. That's probably overstating it, but not by much. And so those people are extraordinarily valuable to a large number of organizations. Your ability to kind of step into the tech without necessarily having to get incredibly deep on that, but be able to share a concept and to be able to share something that is useful within the organizational or the broader social outcomes of that tech. I have been in so many meetings. In fact, most of my career outside of academia has been, my official title in one role was as liaison, as someone who stopped people from yelling at each other in different departments. I've been in so many meetings where I've had technical people just say, oh, that's not possible. Right? Like what you want to do with this is not possible. And in rare cases, that is actually accurate. In a broader set of cases, what they mean to say is that's really hard. Like we would have to change a lot of stuff to make that happen. And in a surprisingly large number of cases, what that really translates as is, I don't want to do that. So having the ability to have someone that can kind of parse through what is being said and understand at least a top level what the technical constraints are is really important. So what do you need for that to happen for someone coming into that program? For someone leaving that program, they do need to have some basic level of statistical ability and some basic level of being able to think programmatically, even if they're not coding. I don't think that people would come into this program and leave expecting to be application programmers, for example, or do system programming. That's not what this is intended to do. Also, this is not really intended to bring people out who are building ML models for the most part. Now that the need for people who can do that is being reduced rapidly as some standards are being built around that. But I don't think that, like, for example, you're going to be publishing, for the most part, this may be true for some of you, but are going to be publishing things in different kind of models for efficiency and different kinds of ML models or training models or whatever, right? That's not really what our focus is. But you should have the ability to think programmatically and to program. That is, you should be able to break something down into the appropriate steps and think about what programs can and can't do and what kinds of structures of data can and can't exist, and issues around efficiency more broadly in data and what some of the constraints on that would be, and interfaces, right? So these kinds of basic fluency in this stuff is useful. Moreover, as anyone with a social science background or a technical background, you should have basic fluency in how we think about statistical methods. Even if that is changing a little bit in the data science world, especially around questions of samples and populations. So when people apply to the program, you are not required to have any stats or programming background. That may change in the future. At the very least, it may change in terms of the requirements once you get in. Even if that's not a requirement of the program, I would strongly urge you to get to the point where you have a basic competency in these two. My thought is that at least in the version of 510, if you manage to survive your way through that in a passable form, you have at least the basics of being able to do that through 510, 550, and 551. This is, again, in the SDS program. We don't really right now at least have an explicit statistics expectation. And I think some have tried to teach that in here, and I'm going to punt that and say I'm not going to teach it here. I really struggled with this, whether I could do, stats in a week. And I know I can't, and that would have been this week. And I know I can't do that. So instead, I'm going to punt as well. But what I will say is that you should have some basic statistical competence and some basic level of recognizing, there are different levels of knowing something, right? Of being able to recognize and read a statistical analysis and see whether it makes sense to you, understand what's being done, so that, that observability level, maybe to be able to critique it a little, maybe to be able to do your own stats at some level. And there's different kinds of techniques here. There's some stats that I would have to sit down and study before I could do, for sure. And so like, but there are some things that I could do in my sleep, right? So at some level, there are things you should be able to observe, things you should know exist, I guess, would be the very lowest level. I know that this is there, things where you can kind of understand what's going on. And then when you can do it, and then when you, I guess the top level, can you innovate in this particular area? Can you come up with a new technique that people haven't used before that is effective in a new way? All right. So what does that look like? What do you need to understand? At a very basic level, you need to understand, obviously in a social data science program, what data is and how it's recorded. So this is, even though it tends towards the more data structured side, variables and data structure side, you have to understand kind of how variables can be recorded, right? And we've talked about that already in this course and probably in other courses around how you can record counts, how you can record binary data, how you can record categorical data, how you can record this in different kinds of data structures, linked, maybe you haven't talked about linked lists because that doesn't really matter, but database systems and things like that, right? How you can deal with things that are in a list, how you can sort those lists, all of those kinds of things. So at some level, what variables are and how we can record them in a digital setting is a really essential piece. I don't know that I'd call that statistics, but it is vital to the process of doing stats, right? Then at some level, summarizing statistics. That is, can you take two variables and throw them into a scatter plot? I know someone who took stats at the undergraduate level and had his stats teacher get up on the desk and say, I'm going to get up on the desk right now and jump up and down and tell you must always put your variables into a scatter plot. And then he got up on the desk and he jumped up and down and said, always put your variables into a scatter plot. So, can you engage in descriptive statistics, which is really summarizing what's going on with a collection of values, right? Do you know how to take a mean? Do you know the difference between the mean mode and median, right? These are measures of central tendency. Do you understand why you might want to choose to use a median for something rather than a mode? This gets to one of the other things we do in description, which is how are your counts distributed? Both how are they spread? Are they part of a normal distribution? That is what we consider that bell-shaped curve in terms of how they're distributed against possible sections. This is the other thing you should be doing along with that scatter plot, is a histogram of some sort to see whether you have a normal distribution. That matters a lot for a bunch of other stats you might want to do. How spread out are they? Do you have a bunch of measurements that are within one category, or do you have variance among your measurements that mean that it is, for example, in terms of distribution, you might have a normal distribution, that is the bell-shaped curve, or you might have just a flat distribution where you have a bunch of stuff all over the place, right? In that case, you're going to see that in your measurements of variance. You might have a mean that's right in the middle, but it doesn't really matter if it's flat. If it's not a bell-shaped curve, your mean matters even less if you have a bimodal distribution where you have two peaks, right? So being able to describe the collection of numbers in a way that both talks about central tendency, but then talks about distribution and talks about what we might call skewedness, and talks about things like that. I think that's pretty much essential. I think that in the American system, we hit that pretty early on. I think most people have hit that in grade school. And so maybe not the distributions piece, but at least the kind of mean, median, and mode maybe, and some of these other standard deviation, maybe in some, I don't know where we hit that in schools in the US, but those kinds of basic descriptions of the statistics that describe a general set of data, I think are something that everyone should have. I think you should be able to do that in a language, R or Python, because that's probably what you're going to be using for other kinds of analyses. I think you should be able to extract the data that you need to be able to use to kind of pull it out and do that with it. So some of this is manipulating the data, not just knowing what it is, but being able to manipulate it. I will say, as an offset here, how much of this is black boxed is always a question as well. I came up in a social science program where, for some, they may just say feed it into SPSS and it'll give you an answer. Hopefully you don't need to do that for means or medians. You can figure out how to do that without relying on a function to do it for you. Now, I don't sit down and hand calculate means, right? I throw that in and I say, what's the average of all this? But you should know kind of how that is calculated. So somewhere in your head, you should understand this is, you can use calculators, but you should understand what 5 times 5 is without multiplying them. It's the same kind of thing. You can use these systems to do all of this, but you should understand what's happening in the black box behind. At some point, that becomes less important, I think, but where that line is a little tricky. In some cases, it becomes impossible, especially as we get into machine learning. We don't know what's in the black box, and neither does it. This is some of the work right now is around explainable AI, around figuring out how it is you come up with predictions, for example. Okay, so that is descriptive stats, being able to describe at a basic level what's going on in a collection of data you have. The tradition for a very long time in sociology and in a lot of the social sciences was to collect data from a sample and then infer from that sample to the population at large. Really quickly, in case it's been a while, generally for inferential statistics, you have a population, say the population of the United States as a whole, and then you draw a sample from that. A bunch of ways you can draw a sample. The most basic way is a random sample, where you just kind of pick people out. You can do striated samples. You can do, interval samples where you take every nth person. You can do some kind of stratified sample where you say, okay, I'm going to sample, but I need to make sure that I know something about the population as a whole. For example, I have IRS records or I have census data that tells me that there are 51% of, I don't know what it is offhand, but 51% of Americans are women. So I want to make sure that my sample also has 51% women because that's more likely to be representative. The whole idea here is that your sample is representative. People will talk about convenient samples or kind of non-representative samples in various kinds. And that means what that means is that you can't use inferential statistics on it. I mean, you've basically messed up the basic assumption of inferential statistics is that your sample is as close to representative of the whole as possible. As soon as you move away from that, it weakens any kind of inference that you can make from the sample to the whole. But moving forward with the idea that the sample is representative of the whole, the question is, if I can measure something within that sample, how likely it is that the measurement I've made in that sample is reflective of the whole. So if I have 10 Americans in a room, and they have been randomly sampled from the population of the United States, and I take the mean of their height, how likely is it that the mean of their height is found in the population as a whole? And it depends. With 10 people, honestly, it's probably not terrible. But if there's like one or two people from, of Norwegian descent or of Dutch descent, that's going to mess us up, right? So it's going to skew us up towards the top, just because one or two people can make a big difference. The smaller number you have, the larger the error is between being able to infer from the front to the back. Let's do this something different and say, if I measure all the women in the room, if I have five women and 5 men, probably a good assumption if I've sampled randomly that I will get close to that. If I have 5 women and 5 men, and I notice that there's a 1 foot difference between the two, and I make the claim that that would be a really weird thing if there was 1 foot difference, but bear with me. I make the claim that men are taller than women based on this sample of 10 people. Can I then infer that that's true about the population as a whole? And the answer is generally yes, but within certain boundaries of error. And so being able to do that, being able to think about the various tests for determining whether this is, basically hypothesis testing, whether the data you have actually disproves a null hypothesis, is a pretty core process for social scientists. And so to understand why that works, you probably have to have a decent understanding of probability, which is a big chunk of this. That understanding of distributions and probability is actually probably more important now than it has been in the past. The reason is that probability distributions have an outsized influence on understanding things like machine learning, which are really just a question of determining the probability of something happening randomly versus having meaningful connection. And so understanding, if you take a basic stats class, you're going to hit contingent probabilities and questions of the Bayes theorem and stuff like that. And honestly, it will matter a little to understanding why inferential stats works. But it turns out that we aren't going to be using inferential stats to the same degree when we're collecting big data, because it's not so much a sample of a population, but just an attempt to get the entire population, ideally. So I think that a lot of the tools that are basic to social science are still worth learning. You should still understand when you see that p-value, what it means and what they're saying about their inferential ability. But I think it is a slightly less important to those who are going to be mostly engaged in data science, because we are mostly going to be dealing with populations and not samples. And so I think there's a slight diminution of that kind of hypothesis testing of inferring from a sample to the whole. The other piece of that is questions around correlation. And so being able to correlate 2 values or being able to correlate multiple values and figure out how they are connected to one another is also a core piece of what people do. This is things like linear regressions and things like multiple linear regressions, but also regressing to more complex kinds of descriptions of that data and looking at models that look at causation at different levels. That last piece happens mostly in psychology. You don't see a lot of that in other places necessarily. And I don't know that it's essential that you learn to do that for the kinds of things that we mostly do in data science, but I will note that it's there. I think that if you have those basic concepts and importantly understand not just how to do them, not the process of doing it, but some of the ways of thinking that get you there, right? The kinds of choices you make to decide how to use those analyses, that's probably enough. That's probably enough, especially until you find a case where you need something else. For example, I never learned how to deal with largely pathway data and nominal pathway data. Now, if you had taken a biostats program, that kind of question of pathway data would be really important, especially for studies of things in biostatistics and maybe genetics. These are things that are, ordinal patterns, right? That things happen, this happens, and this happens, and this happens. Or maybe, how do I navigate from this point to this point? And you have a whole bunch of people navigating from this point to this point, and they may all take different paths. How can you categorize those paths? This is something you're not going to learn in a basic stats class, and I never learned. And so I had to learn it on the job, right? Like I had a set of data where I could look at pathways by which people had done certain milestones. And if I wanted to be able to describe that in a useful way that could both inform questions like, well, let's take this this isn't exactly what I was doing, but it's kind of a parallel question. Like, what courses should you take in a university? So I could take the collection of all of your transcripts and then try to figure out who was really successful in the back end, and then were their pathways useful, right? So if I wanted to compare let's say we have people that got that I don't know, got some kind of, you could cut this into two groups, the super successful and the, let's say, less successful in either job searches or income or accomplishments or publications or, whatever. We find some end metric that says whether someone is successful or not. We split our group into two halves, and then we look at the pathways of the courses they took in university, for example, by looking at their transcripts. Now, can you find some median pathway from one group and median pathway from the other group and make some determination as to how these two are different? That's nothing that's taught as a standard thing, right? That's not something that is going to be in your bog standard stats class, but it's something you'll have to pick up. And you can take a class in this for sure. You can go talk to a statistician who will walk you through it. You can go read some other people who have done something like this and then figure out backwards how you get there. But the essential pieces of this is that there are pieces here where, it doesn't make sense to learn it ahead of time. The big conceptual kind of foundation you probably should have, but these very detailed kinds of questions about how to do particular kinds of problem solving with data is something you'll have to be comfortable with muddling through. So let's assume that you didn't have, 3 or 4 courses in your undergrad or 3 or 4 courses in your grad programs on stats or 5 or 6 courses in this. How are you going to come up to speed? And I would say, let's start with the kind of basic literacy piece. You can take a class. Right? There's a class there's a couple of classes we can recommend. There's one that is being taught right now in our kind of in a slightly cognate program in our own school in behavioral data science and in biological data science also in our own college. Both of them use R, but they are both very good kind of quick rundowns from descriptive to inferential to some kinds of regression that get you the basic tools. And honestly, I think for most of you, I would recommend that if you have not had it or you have not had it in a while. I will tell you from personal experience that stats classes can be either hell and horrible, or kind of, if you are lucky enough to have someone who really loves stats. I don't really love stats. If you're lucky to have someone who really loves stats and loves teaching stats to people who don't necessarily love stats, then you really luck out, because they will really kind of take seriously this idea of engaging you with the ideas and not just getting you through the process. And so that's useful. But that's kind of hit or miss. I haven't taken these courses at our university. I can't tell you for sure who does that well. So it's kind of, you have to hope that you're hitting one. That said, I think for most people, taking this as a course is the way to go. There's a book, which I don't know, I may have a cover here. I have it on a shelf over there, called Practical Statistics for Data Scientists. I may actually assign you kind of the first couple of chapters of that to look over, especially if you don't have a background in stats. And I think it's actually pretty good. It runs through it pretty quickly. It's not as much conceptual as it is working through it. But I have to say, one of the things it does well is it engages you in examples. Do not just read something. If you're going to take a book like this, go out and find some data and play with it. You have to go through doing this to understand it. It will just bounce. You might get it, but it will bounce off your brain if you do not sit down with some data and mess with it as you're going through the book. So I will point you to another one, which is one that takes you through it in Python particularly. And if you already have experience with Python, you can actually go through their examples and do parallel examples and try out some of the stuff. Make sure that you're understanding kind of how this process works. So I would say that's also very useful. There are a number of online courses as well. Code Academy has one. University of Michigan has one in Coursera. I would tend towards the ones that are meant for like stats for data science. Surprisingly, a lot of these are really basic, but that's okay, especially if you need that. And so that can be useful. There are a couple of possibilities on YouTube too, although I have found those to be far less useful than being able to sit down with either a course or a book. If you haven't played with Codecademy before, it actually gives you a code screen where you can run basic code in a window, and that's kind of a useful way to force you to be playing with the data as you go. But there are other possibilities as well. It's not like Latin, right? I mean, it's not going to make you a better person for having pushed yourself through getting through this, but it is practically pretty important. And so you do not want to be in a position where you're on a team and people are presenting kind of some statistical analyses and you are lost. This is what you want to avoid. So some level of fluency is vital. The amount of fluency you need depends a lot on the kind of work you expect to do and the kind of roles you expect to inhabit in an organization. And so there is not a one size fits all on this front, but that basic fluency I do want to encourage you strongly to acquire, and I can't give it to you in this course. So there's my I guess apologia and apology at the same time. So learn some stats, just not right here. All right, thanks.